Hello everyone, my name is Youssef and I will be presenting to you our work, Have We Ever Encountered This Before? Retrieving Out-of-Distribution Road Obstacles from Driving Scenes. So let's first start with an example of some OOD road obstacles in the real world and why this actually causes a significant safety challenge. So basically, road obstacles can be any object that fall on the drivable area of the road, whether it's road debris, whether it's wildlife crossing the road. It can be basically anything. So the root of this problem is the current state-of-the-art supervised learning methods rely on a closed world assumption. And this is basically that it's trained to detect a set of predefined classes, and it only gives us some guarantee on these predefined classes. However, when it encounters an object that falls outside of these classes, we basically have no guarantees. So what I'll show you here is an example of a state-of-the-art object detector mounted on a vehicle in a parking lot. So as you can see, cars are detected pretty well, but once a shopping cart appears, this is actually just missed by our detector because the model was never trained to detect shopping carts. So basically you see here that pedestrians and vehicles are detected well because this is basically what we have, what we trained the model on. But for unknown classes, such as the shopping cart, these are just missed by the network. So now imagine the following scenario. We have our self-driving vehicle on the road. Then it encounters a shopping cart, and as we saw in the previous example, the shopping cart is just not detected, and as a result, our vehicle bumps into this shopping cart. So now, if we want to solve this problem, the first question we would ask is, have we ever encountered this before? Do we have similar data of encounters with shopping carts such that we can find out where the root cause of the problem is and how can we actually solve this problem? We can formulate our problem as the following. Given an uncurated dataset, which is basically an unlabeled dataset, and a text query, how can we retrieve all the segments in the dataset that match the text query? Of course, in this setting, we are limited to only OOD road obstacles because this is exactly our use case. So we now face two challenges. One is how can we efficiently detect OOD objects in video streams and get the entire segment where the OOD object is present? And then the second one is how to actually retrieve all the OOD objects that match our given text query. So now our approach is the following. Given the unlabeled videos, we first try to segment and track each OOD road obstacle instance. And then once the user gives a text query for the item he is searching for, we try to retrieve all the instances of objects matching this query. Our approach has three main steps, basically the OOD segmentation, the OOD tracking, and finally the text-based retrieval. So let's start with the OOD segmentation pipeline. So we get as input a single frame of an OOD image. We pass this image through the segmentation network, and in our work we used a mask-to-former segmentation network with the rejected by all scoring function for detecting the out-of-distribution pixels. And then basically from the segmentation network, we can extract the road mask, and using the RBA scoring function, we can extract the OOD mask. Then the OOD mask is passed through a meta-classification. And basically what meta-classification does, it's a binary classification model that's added on top of the segmentation model to eliminate some of the false positive predictions. It utilizes some of the known features, such as the segment entropy, the variation ratio, the probability margin, the segment size, and the ratio between the interior and boundary, such that it detects what is actually an object and what is a false prediction. Then the second step is like utilizing the road mask to create a region of interest. So objects on the road are either misclassified as being a wrong object, or they're actually not detected at all, and they're just blended with the road. So we can restrict our predictions from the OOD mask to only objects that lie on the road. But we do not have a perfect road mask. So we get the road mask, and then we have to morphologically close any of the gaps that we get in the road mask, because if there's an OOD obstacle, maybe it's missed, but maybe it's misdetected as being something else. So we morphologically close the mask to define a region of interest. And then this region of interest is used to limit the predictions of the OOD objects to being only the OOD objects on the road, which is our road obstacles, OOD road obstacles. The second step in our framework is the OOD tracking. For OOD tracking, we follow the tracking by detection paradigm. We combine the OOD road obstacle segmentation pipeline we showed in the previous slide with an IOU tracker. The IOU tracker takes all the OOD road obstacle segments in each frame and tries to match the detections across the sequence of frames. The final processing step of our framework is a text-based retrieval, and for that we utilize a multi-modal feature encoder, which has two modalities, text and image, and embeds both of these into a joint feature space. So we utilize first the OOD road obstacle segments, which we get from the very first processing step, to get all the OOD road obstacle embeddings. Then we utilize the tracking information to create a linkage between all the OOD road obstacles embeddings, thus creating a vector for each OOD road obstacle segment. Then the user gives in the text query for the segment he's actually searching for. This text query is then embedded into the same feature space, and then any OOD road obstacle embedding that is similar to the text query is then retrieved. And then the entire segment, which has at least one OOD road obstacle embedding retrieved, is considered to be retrieved. And then we get the full OOD road obstacles segments. Now for our findings. We found out that actually object-level processing is necessary for this retrieval pipeline. We compared feeding in the entire scene with feeding in only the detected crops, which we get from the very first step of our framework, which is the OOD road obstacle segmentation. And we found out that the retrieval pipeline works a lot better for when it's on object level rather than on a full scene level. We also found out that tracking has two benefits. The first benefit is it can be used to eliminate some of the false positive detections, because you can basically put a limit on how long an object needs to stay in the frame for it to actually be an OOD obstacle and not just be a one-time false positive. And the second thing is we found out that it actually helps the retrieval pipeline, since it's usually a lot harder to retrieve small crops than to retrieve bigger objects. So the tracking helps us create a connection between the small object and the big object and allows us to have an easier retrieval pipeline. The third finding was actually false positives propagate through the networks and cause a lot of errors. So we need to have some measures to actually reduce the false positives as much as possible. As a summary, we present a modular and systematic approach for retrieving out-of-distribution road obstacles from driving scenes using text queries. Our approach utilizes three processing steps. 1. Identifying OOD road obstacles in singular frames. 2. Tracking OOD road obstacles across the frames. And 3. Enabling textual queries of OOD road obstacle video sequences using a multimodal feature embedding space. We show that tracking information actually enhances this pipeline by improving the detections and improving the retrieval. And we also show that the multimodal embedding space generates clusters of OOD road obstacles in a low-dimensional feature embedding space, thus enabling proper text-to-video retrieval based on semantic similarities rather than just visual similarities, which you'd get from only using singular modality feature encoder. Thank you.